What if we could see the universe through gravity eyes? The frontier in astronomical detection is the detection of gravity waves. Essentially, everything we know about the universe comes from electromagnetic radiation of different kinds. But the universe contains stuff, and there is a possibility to see the stuff directly. In general relativity, Einstein's theory of gravity, anytime a mass distribution changes, it releases ripples into space-time that travel outward at the speed of light. These signals propagate through the universe, even passing through matter as if it weren't there, because they are essentially distortions or waves in space-time itself. Gravity waves are conceptually difficult to understand, because of course we don't see space. But if we could look at a grid that physically represented the invisible space and watched it distort as a gravity wave passed through it, we'd see that gravity waves have all the properties of normal waves. They can be compression and rarefaction waves like sound waves, or transverse waves like light waves. These signals travel through the universe at light speed anytime a mass distribution changes. That could be, for example, because a star contracts to a new situation, or explodes at the end of its life, or a black hole forms, or swallows some material. Or gravity waves could be produced in the incredible gravity regime of the early universe, when the mass distribution is changing rapidly due to the expansion of space-time. In this simulation, space-time is visualized as two neutron stars are in a tight orbit around each other. They lose energy by gravitational radiation, which travels away at the speed of light. And then, as the neutron stars coalesce and form a single black hole, a torrent of gravity waves are produced. These signatures are predicted exactly by general relativity, so there's no theoretical uncertainty as to what gravity waves should look like, if you could only detect them. The detection of gravity waves is an enormous challenge. Remember, they are predicted by our good theory of gravity, general relativity, that's passed all of its tests so far with flying colors. One example of a way they might be detected is, imagine a situation where not just two small compact objects, but two huge compact objects are coalescing somewhere far off in space. In this case, two galaxies are slowly colliding and coalescing, and their central black holes are merging. That merger produces an enormous torrent of gravity waves traveling out at the speed of light. The gravity waves travel through space, and millions of years later, they reach the Earth. One idea of how to detect these gravity waves is to use pulsars. We can find pulsars in almost every direction in the sky. They're exquisitely accurate clocks, accurate to 1 part in 10 to the 15. But when a gravity wave passes through a pulsar, it glitches or changes the spin rate of the pulsar subtly, but detectably to a radio telescope. So in this concept of the detection of gravity waves, we use a grid of pulsars in our own galaxy to detect the passage of gravity waves through our galaxy, originating from a distant coalescing supermassive black hole. This is quite exotic, and no one's ever demonstrated how this might work in practice, but it's a concept of how gravity waves might be detected. That's very hypothetical, but physicists have come up with an actual physical experiment to detect gravity waves. It's not familiar to the general public, but this project, which cost nearly $1 billion, is ready for routine science operation. Its acronym is LIGO, the Laser Interferometer Gravitational Observatory. LIGO is an extraordinary scientific experiment designed to detect these minute distortions in space-time as they arrive at the Earth from distant astronomical events. Knowing how invisible all these distortions and effects are, imagine the skepticism of a funding agency or a member of Congress being asked to foot the bill for $1 billion project to detect something invisible and difficult to comprehend. The LIGO scientists have managed this. Their project is fully funded. The core scientists operate out of Caltech and MIT, home to two of the best gravitational research groups in the world. LIGO is a twin detector. One is situated in Livingston, in the southeast part of the United States, and the other is situated in Hanford, in the northwest. Two detectors are needed because the signals are so subtle and so easy to confuse with noise that you would need the simultaneous detection of an astronomical signal by the two separated detectors before you'd be confident you detected something real. In fact, the partners have been able to persuade European collaborations to build a third detector. With 3 detectors, you have some possibility of determining the direction of origin of the gravitational waves. a critical piece of information given that the object that gives rise to the signal may be invisible or hard to detect with optical telescopes. Viewed from the air, these detectors are enormous undertakings. They are basically two arms, each 5 kilometers long, where light travels up and down through a vacuum tube, one of the best vacuums it can be possible to create on the Earth, in fact. The light is then combined in something called an interferometer, which is sensitive to tiny changes in the path length of one of the two arms. Interferometry is a fairly standard technique in the lab, but no one has yet executed an interferometer on this huge scale, a 5 kilometer long interferometer. Light travels up and down each of the arms hundreds or thousands of times before it's combined and interference fringes are sought. The critical part of the detector is a solid metal mass, extremely accurately known both in its dimension and its mass, which has a mirror attached. If this mass changes shape or size in any way, it feeds into the signal in the interferometer and will change the fringing patterns seen at the Michelson interferometer. The concept of the experiment, therefore, is to look for a tiny distortion of this test mass, something about 1 meter long, made out of pure metal, caused by the passage of a gravitational wave through it from a distant source. Doing this experiment requires extraordinary technology. The optical surfaces in the interferometer are as accurate as we know how to make optical surfaces. What might a gravity wave detector see? It would be hardly worth spending $1 billion on an experiment like this unless you were pretty confident there was something to detect. Astrophysicists are confident because gravity wave theorists have calculated what happens when two neutron stars combine, or a neutron star and a black hole, or two black holes. Since stars routinely form in binary pairs, we know that neutron star pairs and black hole pairs exist in the galaxy. In fact, there are probably 50 million neutron star binaries and 10 million black hole binaries in the entire Milky Way. These binaries will lose energy by the release of modest amounts of gravitational energy and inspiral towards each other. But the real signal that LIGO is looking for is when they coalesce and merge into a single black hole. Then there will be an enormous spike in the intensity and level of the gravity waves, and that's what LIGO is designed to detect. LIGO can also look at other interesting signals, such as the death throes of a star. LIGO is also hoping to detect signals from the very early universe, when the gravity situation was also changing rapidly just after the Big Bang. Finally, there are things that LIGO doesn't know how to detect because we haven't predicted them. Every scientific experiment that opens up a new regime of observation finds things that weren't predicted, and LIGO scientists are extremely excited to observe the universe in a fundamentally new way. The sensitivity of LIGO is bounded in two sides in frequency, because the fundamental issue of the gravity wave is how rapidly it varies, how rapidly the space-time is changing. The low bound on frequency for LIGO detection is geological noise. Even in a geologically quiet place, like Hanford and Livingston, both chosen for that reason, there's mild geological noise at the level of a few hertz. It's unavoidable and there's no way to compensate for it. And that rising geological noise prevents LIGO from detecting very slow gravity wave oscillations. Towards higher frequencies, like 100 or 1000 hertz, the limitation on LIGO is pure electronic noise, also unavoidable, however quiet your electronics. The figure of merit of LIGO is an extraordinary number, a dimensionless number of 10 to the minus 22. That's 1 part in 100,000 billion. That's the level at which LIGO is detecting space-time distortions. If you imagine that test mass about 1 meter long, that large block of metal, you're looking for a variation in its length smaller than the width of a proton. It sounds extraordinary, it sounds impossible, but LIGO has shown in the last few years that it can do this. To the people who've built LIGO, this will be a profound moment. What will LIGO find? Essentially, there are only two possibilities, both of which are interesting. One possibility is that the predictions of neutron star and black hole inspirals are correct, and LIGO will be able to see these events out to distances of tens of millions of light years. Based on the numbers of these objects, LIGO predicts that they will detect about 1 or 2 events per week. And so in its first year, LIGO will have 100 gravity wave events detected. But what if something is wrong in our theory of gravity? What if LIGO detects nothing? But to the theorists involved, that would be almost as interesting, because if LIGO finds nothing, that means our theory of gravity is fundamentally wrong. Einstein's general relativity has never been tested in this regime, the regime of strong gravity, and never have we been able to look directly for the distortions in space-time So if LIGO fails, we will have learned that our gravity theory is wrong and needs to be replaced, and the theorist will get to work. Meanwhile, there's a space mission designed to do things that LIGO cannot do. Its name is LISA, the acronym standing for the Laser Interferometry Space Antenna. LISA is a free-floating set of 3 antennas that combine their information through space and form interferometry that way. The technology to do this is challenging, but NASA's shown that it's possible. If we have LIGO, why do we need LISA? Because LISA will observe an entirely different regime of gravity waves. Remember that LIGO's sensitivity is bounded very strongly at the low frequency end by geological noise. There's no way to look for slower or lower frequency gravity waves. In space, the stability of the environment allows extremely low frequency gravity waves to be detected. And if you imagine large masses coalescing or colliding, much larger than stars, their frequency of their gravity waves is proportionally slower. So LISA is designed to look at the mergers of massive black holes, the kind that inhabit the center of galaxies, whereas LIGO is designed to look at the merger and coalescence of normal mass black holes, the kind that are left behind when a massive star dies. Between them, they'll cover a regime ranging over factors of millions in the frequency of the gravity waves. The final frontier of observational astronomy is the detection of gravity waves. These distortions of space-time are predicted out of general relativity, Einstein's theory of gravity. Anytime a mass changes in the universe, it should release subtle gravitational distortions of space-time that travel outward at the speed of light. A project that will start taking science data in 2014, called LIGO, hopes to detect these minute distortions, which will reveal the universe of colliding black holes and neutron stars, and perhaps signatures from the early universe itself.